Okay, so like I was saying, it's very, very easy for one not to, know so much mathematics or statistics, and the person still excels as a data analyst. Okay, because basically what you'll be doing, working with are just basic, um, aggregations and all of that, and most of them the system helps you with those operations. Now, when you come into data science, it's a lot more different, because even if you run statistical models and all of that, and you generate output or result, you need to be able to understand what you have. You need to be able to make sense of the output and be able to interpret what is coming out of that output for you, whether you're using Python or R or any local no-code platform. It's going to generate output. It will show you F statistics. It will show you R square. It will show you a lot of things. Okay. How do you understand what those things mean? How do you understand? How do you know if your model is doing fine or not? Okay. How do you know if the data set you're working with is normal, or it is skewed, or it has outlier, or it has issues? Okay, how do you know the kind of transformation that you need to further apply to your process, if you don't even understand the problem that your data have based on the output? Do you understand? So you can't run away from your basic understanding of statistics, probability, and all of that. So today I'm going to take you all through some other aspects of, statistics. And we'll look at the interquartile range, we'll look at skewness, and we'll look at kurtosis. I think that is the three main things we are going to look at for tonight. And next Sunday, maybe we'll take one more class on statistics, then we go into probability. Okay, so let's start with what we have today. So for today, like I said, we'll look at the interquartile range. The interquartile range is a very, very important statistic. Okay, please admit somebody that comes in. You're free to. Now, when we look at the interquartile range, what do we mean? What are we talking about? We're talking about a range of data, like the distribution of our data, right? Around the mean, somehow around the mean is still part of descriptive statistics. Now, the for instance, you have a data set, and then you have this data set in quartiles. Quartiles means that the frequency or the distribution of the data is divided into 4 equal parts, right? Of 25% each, 25, 25, 25, 25 quartiles into 4 equal parts. So the measures within the middle, okay, looking at, let's say, the second quartile and the third quartile, right, is our interquartile range. Okay, so is the range for the middle, or or the mid 50% of the data. Like I said, you have a data set running from, let's say, 1 to 100, and then you arrange them. Your first quartile is the first 25. Your second quartile is from 26 to 50. Then from 51 to 75, your third quartile from 76 to 100, something like that, right? So you have 4 quadrants of 25% each. Okay. Now, your interquartile range falls within the 50th percentile, okay, or the middle, anywhere within the second and third quartile, or the difference between the third and the first quartile. Okay, when you have Q3 minus Q1, so the 75th percentile minus the first percentile, Okay, so somewhere lying in the middle or the median. All right. So the interquartile range tells you the spread of the middle half of your distribution. Last week, we talked about a little bit about um, normal distribution. We're going to look at it more um, in more detail this evening. Okay, so I'll run through the slides and then we take your questions. Okay. All right. So yes, this is what I mean. This is the IQR, the interquartile range. Notice that we have four quartiles here. Okay, so we have yeah, four quartiles of 25% each. So quartiles segment any distribution that's ordered from low to high into four equal parts, like I've explained, where you have data set from 1 to 100. Okay, so the interquartile range contains the second and third quartiles. Yeah, between here and here. Okay, somewhere in the middle. This is our interquartile range, anywhere between here and here. Okay, so that is why I said the difference between Q3 and Q1 is our interquartile range. All right. Um, so what are the benefits of the interquartile range in statistics or machine learning or data science? What are the benefits? First of all, along the median, the IQR can give you an overview of where most of your values lie and how clustered they are. Remember, the last time we had our class, we talked about clusters. Okay, we talked about where we use the line of best fit. Okay, to look at the distance between each of the data points from the mean. When we're looking at the variance, the difference between each of the data points from the mean. Okay, now we are looking at the mean. We are looking at an overview, the cluster, how our data set revolves around the mean. Okay, that is what we are looking at with our interquartile. So the interquartile range gives us the overview of how our data is clustered around the middle value or the median. Now, the ICAR is also useful for data sets with outliers. We talked about outliers too, where you have data sets that are not even close to the mean at all or the median. You have data sets that are very, very far away, okay, or far, let's say far off from the range of the median value. For instance, for instance, so let's say let's say you're a teacher, right? And then you teach people from your class. The class you take takes people of ages 20 to 25. Ages 20 to 25 are your student age range. Now, you now have this session that someone that is 40 or someone that is 10 registers for your class or is coming to register for your class. Maybe for whatever reason, um, you may decide to, okay, let me give them a chance or a trial or something. Now, usually the mean of the age of your students are usually around that, let's say 22, 22.5, 23, right? Now, because of this large variability in the age that you now have for the new, you have someone that is 45 or even 50, or you have someone that is 10 or 12, something like that. They are outliers. They do not fall within the category of your usual data, right? Or within the mean or the median or whatever. So for data sets that have outliers, especially when you use something like a box and whisker, a box and whisker chart like this. This is a box and whisker chart, right? It's going to show you that, okay, oh, normally it will distribute your data into four quadrants or quartiles. Okay, the first one, this place is not where it is measuring. This is the first quartile. This is the fourth quartile. The second and the third are what we have in the box. So the box is what actually the two boxes, right, is the middle point, the second and the third quartile, right, or the difference between the third and the first, however you want to take it, right? So this is what measures your interquartile range. Now, notice that outliers, we have outliers lower than the fence and outliers above the upper fence. Outliers outside the lower fence and outside the upper fence. So if you have a data set that is normally supposed to run from 1 to 100, and then you now have some data points that are 500 and something, 900 and something, they are outliers, they are out of the fence. Or maybe your data is supposed to run from 101, or let's say 201 to 300, and you have data sets of 1 or -1 or 2, those are outliers. They are outside the lower fence. Sorry, I'm trying to admit the person that just joined. Okay. All right, so let's continue. So for a box and whisker chart like this, right? How you're going to know the variability or how dispersed your data sets are, right? Your data points are, is by the size or the width of your interquartile range of this box. Okay, so a smaller width of the box means that you have less dispersion, while a larger width means that you have more dispersion. Okay, so let's continue. Let's look at skewness. But before we come to skewness, is there any question around the interquartile range? Any question around the interquartile range? Please drop your question on the chat, or maybe you note it down. All right, so let's go to skewness. Skewness, when we talk about skewness, what does it really mean? What does it really involve? What does it really entail? Okay, so we look at, in skewness, we look at the degree of symmetry or how symmetrical a distribution is. Okay, how is the symmetry of the distribution? Is it normally, is it asymmetrical or not? Do you understand? So the concept of skewness is mainly used to understand the distribution of the data and steps taken to normalize the data for further building of machine learning models. Now, in data science, usually, right, one of the pre-tests that you do before you start other processes is that you check whether the data is properly distributed. Okay, do you have a proper distributed data or not? So a data set that is not properly distributed or that has lots of outliers, like I've explained in the case of our interquartile range, right? You have lots of outliers, right? If you use if you build a model with that kind of data set, you're going to have spurious output or spurious result. Okay, you may end up making decisions or making conclusions on of your finding from a result that is not correct. What do you do? What do you do when you realize that, okay, this data set is not normally distributed? You do what we call normalization. There's something we call normalization. So normalization is something you can do, okay, to reduce the level of variability in your data, right? And handle the outliers. So it will kind of, level the data such that the differences will not be so much. But how do you know that your data needs normalization? How you know that your data set needs normalization is when you look at the skewness. Of course, you're going to, most times it will generate graphs for you, generate graphs and all of that. You look at the graph, the normal distribution, you look at the skew. Oh, this thing is skewed to the left or is skewed to the right. Okay, you do something about it. There are lots of things you can do about it. Sometimes you take the log. Sometimes there are so many things, methods you can do, you can use around normalizing your data. But when you look at the skewness and it is the normal bell curve, what we call the normal curve of life, you know that, okay, your data set is okay, it's good to go. You're going to work with it. And whatever output you have, we assume that is correct. So most of statistical assumptions, predictions, and models is based around the normal curve or the a data set without any form of skewness. Okay, so we look at why we consider skewness, right? I've tried to explain it a bit, but one of the reasons why we consider skewness is that we want to describe the distribution of a variable alongside other descriptive statistics. Okay, so when you run descriptive statistics, one of the applications that does that very well, SPSS. When you use SPSS for, of course, is for um SPSS is for academic, most times it's for academic research. Some people also use it for business analysis. But why it is basically for academic is, of course, you use it to analyze primary data. Remember, primary data are data you generated on your own with surveys, forms, and stuffs like that. And then you code it into the system, right? Now, secondary data is what we are used to in our trainings. Most of, like in BTM, all the data sets you used in BTM, most of them were secondary data because you were not the one that generated it. You got them from a secondary source, so, right? Now, um, if you have a primary data or a survey and then you've first coded them into your SPSS application and you're doing descriptive statistics, one of the things that comes out with it is skewness, kurtosis, and all of that. So sometimes it's just one of those measures that you just look at. To some people, especially in academic research, it may not really make so much sense, but in business data analysis, the proper data analysis, it makes a lot of sense because whatever output you have is going to affect business decisions. And of course, some decisions you make, some data-driven decisions you make, if they are wrong, if they are spurious, it can fold or make the business go bankrupt. So it's something very, very serious that we don't joke with. So it's one of those distributions that you look at in descriptive statistics. It is also used to determine how normally distributed a variable is. So to determine if a variable is normally distributed or not. Remember why I talk about the normal distribution. The normal distribution is important is because you want to be sure that you don't have outliers or there is no so much variability in your data. Okay, yeah. And if that is the case, if it is not normally distributed, what do? Normalization. You normalize your data. So for those of us that have indicated interest for data science, when we talk about normal distribution and we talk about normalizing the data and all of that, you realize that, okay, this is what we mean and this is why we are doing it. Now, this is what a normal distribution is. Like today, I'm not doing a lot of manual drawing. So this is a normal distribution. This is a normal distribution. This is what we call the normal curve of life. Okay, so a normal distribution has zero skew or no skewness. Is an assumption of many statistical procedures, like I've said, are based on a normal distribution. So we believe that if you're working with a data that is normally distributed, okay, whatever findings you have can be relied on, can be reliable, right? So notice how the normal distribution goes. Start, you have a tail, right? And then the tail starts, uh, moves upward and starts falling gradually to the end. Okay, so if you notice in this kind of distribution, you don't have your main data to one side. It is this is the normal bell curve. This shows zero or no skewness. So in this instance, right, like that example of our mean, median, and mode answers that we got when we're solving to some weeks back, recall that our mode and our mean and our median were equal. In that kind of scenario, what we have is a normal distribution. Just a sec. Okay, so let's continue. Yeah, so yeah, this is a normal distribution. So when you plot your data, right, or you're doing some diagnostics on your data set before you start working on it, or some pretest, and then you have this curve, right? Your model generates this curve. Just know that you're good to go. There is no much variability or no skewness in your data. Yeah, so we have a scenario where your data can be negatively or positively skewed. In a scenario where your data is negatively skewed, okay, you have more data points to the right of the curve where the data, um, yeah, to the right of the curve, the data has more large numbers to the right, to the right, to the right. Notice this is that curve. See the first curve. This is the normal curve, right? Everything is around the middle. This middle point is where we have our mean, our median, and mode, right? Like our central tendency. But here you now have a scenario where your mean is less than your median and your median is less than your mode. Okay? Or in reverse, you can say your mode is greater than your median and the median is greater than the mean. So in this kind of scenario, the large values in your data set, the large values, the chunk of your data is skewed towards the right part of the curve. When you see this kind of curve, whether in machine learning or in data science or whatever, right? Whenever you come across this kind of curve, just know that your data is not normally distributed. You need to normalize this data to get this other curve. So this is the negatively skewed data. Now we have the opposite scenario, right? The positively skewed data where most of your data points are, skewed towards the left. Okay, so in this case, the mode, in this case, the mode is actually greater than the median and the median is greater than the mean. Okay, so the mode is greater than the median is greater than the mean. So the mean is less than the median is less than the mode. So this means that more of your data points are to the left of the curve, but the data has very low values in large numbers. Okay, so let's continue. So that's for skewness. So remember, we have the normal curve, then we have the negatively skewed, then we have the positively skewed, which we have in a scenario where all our data points rather are, towards the left of the curve. Okay, so the next thing we'll be looking at is is called kurtosis. Kurtosis is another measure of the variability in descriptive statistics. So now, what do we really measure specifically with kurtosis? We measure the tailedness of a distribution. Okay, so the tailedness is how often outliers occur. Let's go back. Let's look at this curve. This is the peak of this curve. This is the tail. Okay, just a sec. So this is the peak, this is the tail. This is the peak, this is the tail. This is the tail. This is the peak. This one has two tails. Tail, the left tail, the right tail, right? Now, what is the size of the tail? So when we are looking at the kurtosis, we are looking at the tail of the, the thickness of the tail of a particular distribution. So let's go back. So tailedness is how often outliers occur. Remember, at the tail of your curve, what you have are data points that are far from the middle. Do you understand? They are far from the midpoint, either to the left or the right. So excess kurtosis is the tailedness of a distribution relative to a normal distribution. We've looked at the normal distribution. In a scenario where the tail are more or large or thicker, right? In that scenario, we have more data points that are outside the mean, that are outside the median, outside the mode. Do you understand? They are very far away from our center, the midpoint of our data, whether in smaller values or in larger values. Okay, so that tailness is one of the ways we know how well our data is doing. So tails are the tapering ends on either side of a distribution, like I've shown you. They represent the probability or frequency of values that are extremely high or extremely low compared to the mean. Like I said, if you plot, let me see if my pen is writing today. If you plot, so let's say you have data points, let's say you have 5, then you have 6, then you have 4, right? And dot, 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 dot. Maybe you have lots of these numbers. Then you have numbers around 45, right? You have numbers around 45. Don't mind this pen. I didn't want to write with it today, but maybe I still have to. You have numbers around 45, 50, and all of that. Now you have numbers within 45, 46, 47, 48, 49, 50, something like that. Lots of them. Okay. Now, if you take the mean of this kind of value, you're going to be getting something around 40 or 42, something like that, probably, right? Something around that. Now, at the midpoint of your data, when you plot it in a normal curve, right? Don't mind the way it's bent. Oh. Your midpoint, your mean, is going to be somewhere around here. So if you trace it down, somewhere here, you have your 42, right? Or 42.5 or 43, whatever the output. Now, towards this tail here, the thickness of this tail here is dependent on these outliers. So these outliers, these are outliers. 4 is an outlier, 5 is an out, 6 is an outlier. Depending on how plenty they are, is how the slope of this particular curve is going to be at the tail. Do you understand? So you have your 4, you have your 5, you have your 6, and you have your, all 7, all of those numbers here. Okay, this is the tail. These are outliers. If at this other extreme, remember the tail may also be you may also have another tail towards here where you have 99, 98, maybe you may not, right? But even if you have, or you have 100 or 1000, or you say 198, this is also an outlier to the left. Now, the volume of the outlier is going to pull the curve either to the left or the right. Do you understand? Okay, so let's continue. Let me just take this off. So those are how you can know um if your data set is okay, if you have um the right distribution of data to work with. All right, so what is the difference between skewness and kurtosis? You may be wondering, okay, what's now the difference between skewness and kurtosis? Skewness measures the degree of the slope in the frequency distribution, while kurtosis measures the degree of thickness in tails of the distribution. So your skewness does not have anything to do with the tail. Your skewness deals with whether the distribution is moving to the left or to the right. Okay, the peak point, is it at the left or at the right? That is the skewness. Kurtosis is what is looking at the thickness of the tail. Okay, all right, so that's kurtosis. Now let's move on. So there are three main types of kurtosis. We have the platychotic. The chotic is from the kurtosis, so platychotic, mesochotic, and leptochotic. These are the three main types um of kurtosis, right? So for a platychotic, the distributions has low kurtosis, which means that the tails are thin. You don't have so much outliers. You don't have so much variability in the data. That is platychotic. The distributions with low kurtosis, thin tails. Do you get? Thin tails. Now, mesochotic has medium tails. That is what we call our mesochotic is typical, is more like our normal distribution. Okay, so distributions with medium kurtosis are has medium kind of tails. The tails are not too thin, they are not too fat, they are mesochotic, more like our normal distribution. Now, for leptochotic has high kurtosis. Okay, so the distribution with very high kurtosis, what it also means that it has very large outliers. It has very large outliers. If you have this kind of problem in your output, maybe your data science output or your machine learning output, most times they always come out in machine learning output. One of the things you see. Now, oh, sorry about that. Now, if you have a mesochotic, you most likely not need to do anything to it. In some cases, you don't need to do anything. It's okay to work with it. But if you have a platychotic or a leptochotic, you have to do something about it. You have to find a solution, a way to work on the data, normalize it, okay, and make it fit for what you want to achieve. So now let's look at this graph. These are the graphs. Okay, notice this is the leptochotic. This is the mesochotic. Notice that the mesochotic is more like our normal distribution, right? But this is the platychotic. The platychotic has very thin, very small outliers. Can you see? Can you see? So let me show you something. Let me get the pen, show you something. Now let me bring them out. This is the platychotic. The platychotic, look at the tail. focus here. For now, we are focusing here. From here, we are focusing here. Let's focus here. Those are the tails for kurtosis. Here, right? Notice the tails. This is the platycortic. Sorry. This is the platycortic, this purple, right? Very small tail. Can you see? The tail is small. The tails are small. The outliers are not much. The outliers are not much. We have more of the value. So if you have a distribution that is platycortic, let me see. You have a distribution that is platycortic. It's going to be like this. Oh, I didn't get that at all. So you have a distribution that is platycortic. Notice that the bell is wide. Okay, so if you plot a histogram here, okay, most of the data points, the large data points are just going to be somewhere around the middle. A lot of data points here make sense, right? This is more like a normal distribution. This is platycortic. Very okay. Thin tails. Now, if you have mesocortic, normal, sorry, platycortic is not a normal distribution. It has thin tails. Our normal distribution is a mesocortic, right? Now, if you have leptocortic, notice that leptocortic is this big one, the blue, right? This is mesocortic. It has fatter or larger tails. Now, in a scenario like this, see how it is. The values in the middle are small. We have more outliers at the tails. So you have the histogram is going to look like this. Please don't mind this thing, no. That's why I don't like using it. Get a better pen. See plenty dots. Okay. So let me show you what the histogram of a leptocortic is going to look like. The histogram of a leptocortic is going to look this way. It's going to look this way. So you have data points here at the tail, plenty. Then you have smaller data here at the middle. Then you have more data again at this other tail. Do you understand? Something like that. So when you plot this, you're going to have something that slopes, sorry. The middle is going to be very thin and then it slopes down. Sorry. Middle is going to be thin. Not see how thin it is here. See how thin the middle here is. The peak is thin. The peak is thinner than where we have mesocortic and platycortic. Do you get? So this is what it basically looks like. Okay, for the three different kurtosis. Now let's look at scenarios. This table shows us how the different types of kurtosis can be categorized. Okay, how can we categorize the different types of kurtosis in our distributions. So remember, we have the mesocortic, platycortic, and leptocortic, and we look at the tailedness, ways you can identify and categorize them. Look at the tailedness. The mesocortic is the medium-tailed, the platycortic is the thin-tailed, the leptocortic is the fat-tailed, like I've shown you. Now, what is the outlier frequency? The outlier frequency for mesocortic is medium. Okay. The outlier frequency for platycortic is low, and that is why it has thin tails, like I've explained. But for leptocortic, the outlier frequency is very, very high for leptocortic, and that is why it has very large or fat tails. For the kurtosis score, some statistical models will generate for you, right? There are manual ways to solve it. I think it's mean minus median over standard deviation, something like that. But then 3 minus mean minus median over standard, there's a formula for it. But you shouldn't stress yourself about the formula. It's a very simple formula, but you shouldn't stress yourself about the formula, because most times in machine learning data science, what the system will generate for you is values. Sometimes it may not give you shape, right? It may just give you kurtosis score of maybe 0.9, okay, of 2.5 or 2.9, something like that. So kurtosis score of 3 is the moderate or mesocortic. Kurtosis score that is lower than 3 is platycortic, right? Lower than 3, if you have something like 0.5, 2.1, anything less than 3 is platycortic. It means that of course, the what would I say, that the tails are thin, right? It's platycortic. It does not have so much outliers. That's what it means. But kurtosis score that of higher than 3 or greater than 3 is high, and it is fat-tailed, and it is leptocortic, and it means that it has plenty outliers. Okay, so the excess kurtosis here, you have 0 for mesocortic, negative for platycortic, and positive for leptocortic. We can categorize a mesocortic um, distribution as a normal distribution. Okay, platycortic, we can say, okay, it is relatively uniform. There is no much variation or variability in data, because remember, the data points are at the within the middle. Okay, you have more data points around the mean. That is why there are no outliers. So it is more of a uniform data set. But for a leptocortic, it is what we call Laplace, right? Because it is not normally distribution. It is not even in any way. So this is where I'm going to stop for tonight, and I'm going to take your questions. It's already 8 p.m. So let me take your questions. Our time is already up. So let me stop presenting so that I can take your questions. Adefunke and Stephen, is there any question for today? Any question for today? Were you following?